Okay, it looks like we've got 0 minutes remaining for the start of this thing, so we'll try to get started on time. This is our final speaker series for the summer. I was able to attend a couple of them, but most of them seem to correspond with days that I was in the field. So apologies to any speakers that are on the call that I wasn't present for. I certainly wanted to join them. I'm quite looking forward to these. We also have 2 of the Don Gray finalists in the lineup today. And so if you stick around after April's talk, we're hoping to be able to announce the winner. If it's close and we need to have a little bit more deliberation, then that may not be the case. But if you can stick around after April James speaks, then we should be able to announce the winner. Our first speaker today is Larissa from Ryerson on using stable water isotopes to examine stream water contributions and agricultural catchments. So my understanding, Larissa, is that you're going to share your screen. You did some training with Daryl earlier today or yesterday?
Yes.
Okay.
All right. All right. Everyone should be able to see this now, I believe. All right, so I'll get going. So as mentioned, my name is Larissa, and I'm a master's student at Ryerson. My supervisor is Dr. Chris Wellen, and I'll be presenting some of my thesis work with you today. So the title, as mentioned, is Using Stable Water Isotopes to Examine Stream Water Contributions in Agricultural Catchments. So in the field of hydrology, we're all aware that as water moves through a catchment, it transports nutrients along with it, and this has implications for the body of water that receives it. So eutrophication is one of those implications. There's both natural and human-modified pathways that alter the amount of time that water spends on the land. An example of this is tile drainage, which acts to quickly remove water from the land, preventing pooling of water. So the image on the right side there is the different pathways that we're all familiar with. So for isotopes, for stable water isotopes specifically, there's 3 oxygen and 2 stable hydrogen isotopes, and the proportion of these isotopes in a water sample creates a ratio. And so as water moves through a catchment, variations in the ratio are caused by this fractionation. This occurs essentially during phase change. And so there's an image on the right there just showing the difference in phase change. So because we understand it and it's predictable, we are able to use stable water isotopes as a tracer or a signal through a system. So we can use them to tell you how quickly water moves to a stream through a catchment. So if we use the newest, youngest water, so that's typically precipitation in a catchment, and compare that to the stream, which would be a combination of older water, we can see how long it takes to get to the stream. So it's been shown that event scale changes in stream water isotope composition occurs. Of course, this is measured through isotopes, and this indicates that the source of water is changing through an event. So this brings me to my research objective, which determine whether catchments with high tile drainage are dominated by younger or older stream water contributions, but to not only assess this on an annual scale, to look at this on an event scale as well. So I'm going to be looking at whether these dominant contributions change across temporal scales in a catchment, or if they remain constant. So this is an image of my study area. So I'll be looking at 3 sub-catchments across southern Ontario. All of them are dominated by agriculture, and they have a slope of less than 5%, usually less than 2%. And the catchments are quite small, at less than 50 square kilometers, with the smallest being 35 square kilometers. So the blue dots here indicate the headwater stream sites where I'll be looking, and the corresponding yellow cross next to those is where the precipitation will be sampled in the catchment. So as I might have mentioned, all the sites do vary, and that's in regards to soil type and tile drainage. So on the far right side, North Creek has the North Creek catchment has poorly drained heavy clay soils and very, very low to no tile drainage. In the middle, we have Missouri, and that's very well-drained loamy soils with high tile drainage. And on the far, very southwest corner there, the bottom, is Big, which has poorly drained soils with high tile drainage. So they all vary a little bit. So we collected stream samples at a biweekly frequency for base flow conditions. So this would give us an idea of our old water signature. We also collected stream samples during events at a 4-hour interval. And this was in collaboration with the Ministry of Environment, Conservation and Parks. And we collected precipitation data as well as snow data, and this was at a biweekly interval, and this gives us an idea of the newest water entering a catchment. Now, the snowpack samples were only taken during one winter month, and it was more experimental to see what isotope information this would give us during periods of snowmelt, and just kind of to compare that to the stream. So we obtained meteorological data from the Ministry of Environment, Conservation and Parks, which included temperature, humidity, precipitation. And on the bottom right, you see that station. So that's where our precipitation was collected. And it was shown in the previous side by those yellow crosses. Lastly, we obtained discharge data from the Water Survey of Canada at each of the stream sampling locations. So the first thing we noticed when we looked at our bi-weekly stream and precipitation samples, so those like baseline conditions, was that the samples fell mostly along a Great Lakes meteoric waterline. And this indicates to us that there was little instances of evaporation. However, there's an exception. On the right side, when we look at it by site, we see several red and green dots that plot just below the line at the top, which indicates evaporation occurred. So when we break that into seasons and look on the right side, we see that this occurred mostly in summer samples. And this makes sense because there was a period in time during our study where both of those two streams had nearly zero discharge. So it looked like this. So there was a lot of evaporation, and that kind of makes sense. So next, when we separated each site, we took the precipitation and that stream base flow condition and plotted those along a time series. It shows us this cyclic sine pattern, and that's kind of what we expected due to the variations across seasons and temperatures having that impact on fractionation. So when we calculate the ratio of amplitudes of stream against precipitation, this gives us what's called a fraction of young water, and essentially tells us on an annual basis what proportion of that water is attributed to the young water, so precipitation. So when we look on the right side in the blue there, shows us Missouri, and this had the smallest annual contribution of young stream water. This contrasted greatly with North, which is in the green in the middle slot there, which had a very, very high proportion of young water. Next, when we looked at events, we used hydrograph separations to determine the contribution of young water in each event. So each pie graph shows the distribution of contributions of that event. So the blue shows us the old water, the green shows us the new water, and the gray is a part of the event that wasn't captured. So due to isotopes either in the falling limb or the rising limb that we weren't able to capture, that portion of the event unfortunately was unrepresented. So there was one event here that I just marked out with a red X in Missouri, where 43% of the event was not captured. So we discarded that, or we discluded it, sorry, from any further analysis, just because we aren't able to determine what contribution that water was. So overall, mean total contributions in events of young water are shown at the bottom for each site. So again, on the far left side, we see the Missouri average, which was the lowest mean contribution of young water. And in the middle, again, we see North with the highest. So when we look at what the results show, we see the lowest contribution of young water in both events and an annual scale occurred at Missouri. And as a reminder, this was the catchment with high tile drainage and well-drained soils. Big had a moderate amount, but when we compared this with North Creek, which had the highest contribution of young water, this was the catchment with low tile drainage and poorly drained soils. What's interesting is Big Creek also had high amounts of tile drainage and still had a low to moderate contribution of young water, but also had poorly drained soils. So we saw that as the tile drainage and the soils became more well drained, we actually saw lower contributions of young water. So this indicates that in our studied catchments, tile drainage alone did not necessarily indicate the catchment will be dominated by young water, as we previously suspected. So when we look at this, soil type likely complicated the interaction between the water and the drains. And the region experiences freeze-thaw cycles in the fall and spring. So when we did our hydrograph separations for those events, it was clear that snowmelt had a large contribution in our streams that may not have been well represented by our snow collection methods. And although this water isn't considered new as it sits on the landscape for several weeks, we suspect that this contribution was why we did not see a higher proportion of young water during events, because that composition would have had changed since we last took our sample of snow. So the longer it sat on the landscape, the more it would have fractionated and would have changed the way it would have represented if we didn't sample it right before it melted or as it was melted. We also recognize that young annual and young event water likely has a different age. So young water, as described by the fraction of young water on an annual scale, that was that first analysis with the sine waves that we did, typically is known to have an age of less than 3 months, but during our events, our oldest water was taken at a biweekly interval, and it's possible that it was only a few weeks old. So we suspect that this is why we did not see a higher proportion of young water during events at North when we looked at the event analysis. So in conclusion, we found that catchments in our study with higher tile drainage presence saw lower young water contributions, and we suspect that soil type might have influenced this contribution. So next, we're going to look at moisture conditions and base flow levels before the event to see if that gives us insight into whether that might have some control on the dominant contribution during events, because that could be really important. And understanding contributions and changing contributions of water age may provide insight into event scale water quality changes. So if we see these things change together, this could have implications in the future for nutrient management, and this is something that we'll also consider in the future. And I just would like to acknowledge my lab, everyone from coming out and sampling, the help from the Ministry of Environment, Conservation and Parks, as well as my committee at Ryerson. Thanks.
Okay, great. That was really interesting talk. I'm looking in the chat and in the Q&A to see if there are any questions from the attendees, since you won't be able to unmute yourself. That's not an option. So I'll give maybe a minute for people to possibly pose a question. I do have one, if that's all right, as we wait for other people. So I think you kind of started to address this, but the gray areas on your pie charts, the sort of question mark water, did you try to relate that at all to the antecedent conditions? You sort of started talking about the seasonality and sort of what was happening before, but I should imagine if some of your rain events were the big heavy rain events or more just sort of a slow, steady, 2 or 3 grade drizzly day, did that, even just like qualitatively, did that, match up with what you found at all?
So we started to look at that. So I do know that right now it actually doesn't look like it correlates at all. We've taken the amount of rain during the event, we've taken the amount of rain 2 weeks prior, 1 week prior, as well as the base flow levels. And none of them seem to have a correlation with the amount of event water.
Anything with soil moisture?
I have not looked at that. I do not have that data yet. I can get it, but yeah, it hasn't been something that's definitely something I'm going to look at though. Yeah, I'm assuming it will have a bit of a contribution or effect on the contribution.
Great, thank you. I still don't see any questions in the chat, and we're just about time for our next speaker. All right. So I will set that up. Okay, so our next speaker is Georgina from the University of Toronto, talking about exploring variations in concentration discharge relationships across watersheds in Ontario. So our screen sharing, excellent.
Okay, thanks very much, Pete. I happen to be a deaf speaker and the captionings are not working, so I'm flying a bit deaf, so to speak. So I'm hoping that everybody can both see my screen and hear me. So as mentioned, I'm a PhD student at the University of Toronto, and I'll be talking about some research we're doing on concentration discharge relationships across watersheds in Ontario. So just very quickly, a very quick overview on stream water quality in Ontario. In Ontario, especially in the southern Ontario, we have watersheds that are facing a number of stressors. We have watersheds with very high percent agricultural land cover and urban. And not surprising, in these watersheds, we see that there's poor water quality associated in these watersheds with high stress. A couple of the key issues facing water quality in Ontario. So not surprisingly, with an increasing in urbanization, increasing roadside use, we've seen increasing chloride concentrations in streams over time. And there's also occasions of elevated nutrients in watersheds, particularly we see agriculture and urban. So the factors affecting stream water quality are numerous and complex. There are many different sources, both natural and anthropogenic. And of course, there are many different transport pathways that water can take through a watershed leading to the stream. And in each of these transport pathways, the water takes on an individual chemical signature. And it's the combination of all these sources and transport pathways that we see in the water quality, and specifically the CQ relation. So what do we mean by CQ relation? It's very difficult and very challenging to interpret water quality without taking into account the possible relationship with stream flow. So you can see in the top plot, there's a 2-year hydrograph, and you can see that the red dots are where a water quality sample was taken. And that top plot is showing chloride concentrations. And when you plot concentration against discharge over a long time period, you see whether or not there's a relationship between the concentration and discharge. And this is what we mean by a CQ relationship. So there are three main ways that the CQ relationship can manifest itself if you're considering only a monotonic relationship. So you can see an enriching pattern, which is when concentrations increase with increasing flow. You can see a diluting pattern. This is when concentrations decrease with increasing flow. And you can see a chemostatic pattern. So this is essentially where there's no relationship between concentration and flow. Now, recent studies have found evidence of a breakpoint in slope. So that's to say that instead of these relationships being monotonic, that there could be a breakpoint in the slope, and the slope could change at a certain flow threshold. And so taking this into account, you can end up with 9 different CQ shapes. So why is it important to study CQ shapes? First of all, they have a very practical application. It's necessary to understand the CQ relationships when you're doing load calculations or stream water quality trends. Also, studying these relationships across many different diverse watersheds could provide some insight. For example, watersheds with similar CQ shapes could indicate similar sources and/or transport pathways. The presence of a breakpoint in slope could especially be enlightening, as it could be indicative of different sources or transport pathways between low flow and high flow. And also having this detailed watershed concentration and flow specific knowledge is really essential for effective watershed management. So our research questions: does the CQ relationship vary for different water quality parameters and across watersheds in Ontario? Is slope constant across the entire range of stream flow? What factors may explain the variability in CQ shapes observed? I just realized that I didn't have my screen share. Okay, so my study sites, we have 158 long-term sites were selected that had both stream water quality and flow records for a minimum of 10 years. The study sites spanned a range of land cover uses and sizes. So we had very small watersheds and very large watersheds. In the plot in the bottom right corner, each one of these bars represents an individual watershed. So you could see at the right end of the spectrum, you have watersheds that are very high in agricultural land use. At the left end of the spectrum, you have watersheds very high in forested land cover, a few very urban sites, and of course, a mixture of different land covers and uses. So our methods in terms of determining the CQ relationships. So as I mentioned, long-term stream water quality data was paired with flow for 8 different parameters: total phosphorus, nitrate, suspended solids, chloride, dissolved inorganic carbon, dissolved organic carbon, alkalinity, and calcium. And linear and piecewise regression were used to model the relationship between concentration and flow. And we used a Davy statistical test to first determine whether or not there was an evidence for a breakpoint in the slope. And where there was evidence of a breakpoint, we used piecewise regression to determine the slope both before and after the breakpoint. And the actual shapes were determined by significance of the slope coefficient. So if there was no statistically significant relationship, it was assigned a flat shape. If there was a statistically significant positive slope, it was assigned an up shape. And if there was a statistically significant negative slope, it was assigned a down shape. And watershed characteristics were delineated and characterized using the Ontario Flow Assessment Tool. So one of the pre-screening steps at each of the sites, we developed a flow duration curve. And this was done in order to determine if the range of flow was covered in our paired water quality and flow samples. And at the majority of sites, we were hitting the 5 to 95% range of flow conditions. So our results, so breakpoints and slope. So there's widespread evidence for breakpoints in the slope. Breakpoints in slope were found for each of the water quality parameters tested. Most of the stations had a breakpoint in slope for at least one of the water quality parameters tested. And for the majority of parameters, the predominant change in slope after the breakpoint was a decrease in slope, except for total phosphorus and suspended solids, which had an increase in slope after the breakpoint. So in terms of the CQ shapes that we found, all 9 of the possible CQ shapes were found in our data. And although, and several CQ shapes were found for each of the parameters, although most were represented by just a few dominant shapes. So for suspended solids, dissolved organic carbon, and nitrate, we found an increasing pattern, so an enriching pattern. For alkalinity and calcium, we found an increasing and then decreasing pattern. For total phosphorus, we found a decreasing and then an increasing pattern. And excuse me, for chloride and dissolved inorganic carbon, we found a decreasing pattern. So this slide essentially shows similar results to the slide, to the previous slide, but this one is including some plots, some example plots from our individual sites. So as I mentioned, the dominant pattern for total phosphorus was a decreasing and then increasing pattern. And for suspended solids, we see the dominant pattern was an increase. So this is for these 2 parameters, this is what's to be expected for suspended solids and total phosphorus. We would expect these to be, especially at high flows, mainly driven by erosion and transport processes. Nitrate showed predominantly an increasing pattern. So this was interesting and a little bit unexpected. And there are many possible explanations for this. One possible explanation could be that there are multiple nitrate sources in the watershed, and at higher flow, these sources become greater connected to the stream. And then for chloride, we saw mostly a decreasing pattern. And one possible explanation for when we would see a decreasing pattern, if there's a limited source or mass available of the solute in the watershed, then the effect at a higher flow would be to dilute that concentration. So we're also interested in looking at linkages between the CQ shapes that we found with watershed characteristics. So the first step that was done was to look at box plots between various watershed characteristics and the CQ shapes. So on this slide, I'm just showing one example because, as you can imagine, there are multiple box plots and combinations available. So for this one, we're looking at box plots for total phosphorus and nitrate, and specifically looking at the effect that the percent agricultural land use had on the watershed. So you can see that there's some evidence to support the fact that the watersheds that had mostly an up pattern, an enriching pattern for both total phosphorus and nitrate, tended to be those watersheds that had a higher percentage of agriculture in the watershed. Now, the next step in our analysis of looking at linkages between watershed characteristics and the CQ shapes is to do a classification tree analysis. And the results that we've produced and the numerous watershed characteristics that we have lend themselves very well to this type of analysis. And so it's one thing to look at individual characteristics one by one at the relationships, but what would be even more informative is to look at the combination of factors that could potentially classify and predict CQ shapes. So this diagram, this is just for illustrative purposes. So these are not actual results, but just kind of showing you some of the decisions that the classification tree might be making. So determining which of the watershed characteristics might be the most important in terms of classifying and predicting the CQ shape, and looking at the different splits between these variables, and ideally coming up with a set of combination of watershed characteristics and criteria that would predict the CQ shape for each parameter. So in summary, all 9 possible CQ shapes were found in the data. Several CQ shapes emerged for each water quality parameter, although 2 to 3 predominant shapes emerged. A positive enriching relationship was the predominant CQ shape for nitrate, dissolved organic carbon, and suspended solids. A negative diluting relationship was the predominant CQ shape for dissolved inorganic carbon and chloride. And a relationship with the breakpoint and slope was the dominant CQ shape for total phosphorus, which was down up, and alkalinity and calcium, which was up down. And we found widespread evidence of breakpoints and slope across both watersheds and chemicals. And generally an increase in slope after the breakpoint for total phosphorus in suspended solids, and a decrease in slope after the breakpoint for all other parameters. Now I'd like to acknowledge all the folks that helped with my research along the way. And I'll now take questions. I'm going to stop sharing, and I think we have the closed caption feature available now.
Yeah, so I will look at the chat. I was looking in the question and answer. I was looking in the question and answer section previously, so there are some outstanding questions from the last speaker, but I will see. So we have one question in the chat. Georgina, if you want to read it there, or I can read it out, but it says, I know you touched on this, but can you elaborate a little bit more on what you think causes breakpoints in various water quality parameters? I'm still a little confused.
So there could be several different possible explanations for what could be causing a breakpoint in the slope. So one possible explanation that several authors have theorized and put forward is that at low flow, there's a relatively more importance or contribution of biological drivers to stream water quality, versus once you reach a certain flow threshold, then you're looking at more hydrological drivers of the stream water quality. So those 2 different drivers would result in a very different concentration discharge relationship that we're seeing. Another possible explanation, and these are all just possible explanations, as there could be, and it could be very element specific too. So that the reason for the breakpoint could be different for total phosphorus versus, say, alkalinity. So another possible explanation could be that you just need a certain flow to sort of get that mass of the solute moving into the stream. So maybe you at low flows, you don't see movement of that solute into the streams, and you sort of need to reach a certain threshold where the movement of that solute starts moving into the stream. I could go on, but I think there might be other questions. So
yeah, there was one more question from April on how you interpret the down and then up for total phosphorus. Is it dilution or an enrichment effect?
Yeah, so this one was a bit, there was a few CQ shapes that were definitely a bit puzzling for us to interpret. So one of the, again, these are all just possible explanations, but one thing that we were wondering about with the TP in particular, in terms of that diluting pattern followed by an enriching pattern, was we were wondering if at low flow, there's just sort of a set limit of phosphorus in the stream. So, just a limited amount of phosphorus, of mass of phosphorus. And so at the low flow, once you start to see like the flow slowly increasing, because the mass or the amount doesn't change yet, that slow increase in flow has the effect of causing a dilution. And then once you've passed a certain threshold, then you're seeing sort of potentially erosion and transport processes at play that are now then increasing the concentration. And so that's when you start to see that enriching pattern.
Excellent. Thank you for that. I don't see any other questions. I might just say to Larissa, there were a few questions that I missed from Claire and from Jim, if you wanted to reply in the chat for their benefit and everybody else's. But we will move on to keep our schedule with Wai Ying, looking at hydrological and landscape controls on total and methylmercury export in undisturbed boreal forest headwater catchments. And that's the University of Toronto.
Cool, okay. Let me just get set up here. Okay, I think you can all see that. Thanks for the introduction, Pete. Hi, everyone. My name is Wai, and I'm a PhD student at the University of Toronto under the supervision of Dr. Carl Mitchell. And today I'm going to tell you the story of how I flew to the Dagobah system and learned to use the Force from a Jedi Master. Now, sadly, that isn't true. Although I did journey to a swamp-like land, learned many new things, and now, like Luke at the end of episode 5, I still have a lot of work to do. So today, I'm actually going to be telling you about my work on hydrological and landscape controls on total and methylmercury export in undisturbed boreal forest headwater catchments based on fieldwork in northwestern Ontario. So before I get started, some acknowledgements. First, of course, is Carl. He's my Yoda. Also, everyone in the Mitchell Lab Group who helped with fieldwork, lab work, or data analyses, as well as our study partners at Natural Resources Canada, Ministry of Natural Resources and Forestry, and the Mellis Lab from Ryerson, the KID Lab from McMaster, and our industry partners who participate in and support this work. So there's already been a presentation on aquatic mercury during this virtual conference, but here's a recap for any who weren't able to attend. So mercury is produced naturally by things like volcanic activity, but a lot of what's in the atmosphere today is anthropogenic, coming from sources like coal mining and combustion, industrial effluent, and artisanal gold mining. And once in the atmosphere, it doesn't stay there. It gets deposited into oceans, which is why mercury poisoning from seafood is a major concern in some regions, but also into forests and soils. And Canada's boreal forests have a pretty high capacity for storing mercury. Mercury is a ubiquitous contaminant at low concentrations in Canada's boreal lakes and rivers. And under anaerobic conditions, mercury can be methylated through microbial processes to produce methylmercury, which happens to be a potent neurotoxin with high bioaccumulation and biomagnification potential. And the export of mercury from terrestrial landscapes into adjacent waterways can contribute to high concentrations of mercury in predatory fish, which poses a health risk to humans who consume them. Now, although we know that the boreal forest has an extensive network of waterways and has a high capacity for storing mercury, and that watershed characteristics play some role in controlling total and methylmercury concentrations in receiving waters, there haven't been that many studies that explore hydrological and landscape controls on mercury export across multiple watersheds in the boreal. So kind of to better understand variations in mercury in undisturbed boreal forest catchments, we examined 14 first and second order streams and explored the relationships between mercury and landscape and hydrological variables to try and pick out possible factors governing how and why neighboring watersheds export different mercury loads. So we grouped our study sites into 4 relatively undisturbed forested regions near Dryden, Ontario, and that's not far from the Experimental Lakes area, for those who are familiar with it. And we grouped them based on how we could access them. So 4 are located around Centerfire Lake, 3 around the town of Dinorwic, 4 are accessed by Desert Road, and 3 are accessed by Snowfall Road. And these are the acronyms that you'll see throughout my presentation. So we monitored stream flows from mid-May to mid-October last year and took biweekly water samples and stream chemistry measurements, along with biweekly discharge measurements to develop a stage discharge relationship. And to give kind of a better sense of what each of these regions look like, the Centerfire and Dinorwic clusters are mostly characterized by glaciolacustream deposits and pretty well-drained soils. And the Centerfire sites are mostly these relatively narrow, shallow streams running through forests. So they've got smaller flow volumes and are overall pretty responsive to events. Whereas the Dinorwic sites are also narrow streams, but tend to be deeper, and they run through more open areas. The Desert and Snowfall clumps are very close geographically, and they're mostly characterized by exposed bedrock. The Desert and Snowfall catchments are very similar landscape-wise. They're mostly forests with some rocky outcrops. And all of these photos that you see were taken last fall when the area experienced quite a lot of rain, and you'll see that the flow volumes rise noticeably through September and October. So getting into our results, we see that mercury concentrations were generally low across all sites, similar to other studies in Boreal Canada and in northeastern North America more generally. And total mercury concentrations range from below detection to about 20 ppt, while methyl mercury concentrations range from below detection to 1.2 ppt. And the lowest mean total and methyl mercury concentrations were in the Dinorwic sites. Total mercury concentration we saw was positively correlated with stream flow, likely due to the generally positive relationship between stream flow and DOC, and the generally positive relationship between DOC and total mercury concentration, which we can see here. So both total and methyl mercury concentrations increased with dissolved organic carbon. And this was unsurprising because carbon has long been thought to be an important transport mechanism for mercury. But the relationships between mercury and DOC were not consistent. And several other studies report consistent mercury to DOC ratios, and that's not what we see here. That said, most other studies do only look at 1 or 2 or a handful of watersheds. So kind of looking at this wider comparison that we have, we see that while DOC is an important consideration in mercury mobilization, it's clear that there are also other factors in play. So aside from concentrations, kind of tying into the previous presentation we just saw, we tried to estimate stream mercury loads over the 6-month monitoring period. And previous studies have done this using a concentration to discharge relationship. But we see that methyl mercury in particular doesn't follow discharge especially well. So we used a handful of interpolation methods that use averages as representative measures of concentration for a given time interval for load estimation. So each of these methods has different biases. So the values presented in the slides that follow are averages of these 6 methods normalized by catchment area to give a more straightforward comparison. So we see that methyl mercury loads over the study period were generally higher in the Desert and Snowfall watersheds than in Centerfire and Dinorwic. And this could be for a couple of reasons. The Centerfire and Dinorwic streams are generally shallower than those in Desert and Snowfall. So they may potentially be subject to greater photodemethylation, that's the breakdown of the methyl mercury. And again, the Centerfire and Dinorwic watersheds are also mostly well-drained sandy soils, and that might result in less favorable conditions for anaerobic methylation. We can kind of see a similar pattern in the total mercury loads, with the exception of Dinorwic 3 and Centerfire reference 1. The Centerfire reference 1 site in particular is a bit of an anomaly on the total mercury front because it is in most ways quite similar to the other Centerfire sites, but the area was harvested some 10 years previously, so there could potentially be some very long-term lingering effects, but more study required on that one. we found that total mercury loads were negatively correlated with percent forest cover. And this checks out and it's consistent with previous studies. So in forest ecosystems, inorganic mercury can be stored in plant roots or soils, and that reduces the mercury received by adjacent waterways. Also, we saw that methylmercury was positively correlated with percent wetland cover. Again, this is not especially surprising. Soil and groundwater stores of mercury can be mobilized by the sulfides that are common in the reducing conditions created by wetlands, which often serve as reservoirs of mercury released from upslope areas. And total and methylmercury loads also both increase with stream length, although only total mercury is shown here. And that's likely due to increased inputs of sediment and organic matter via surface runoff. Methylmercury loads was also positively correlated with stream temperatures. Again, this is in line with previous studies. Higher soil and water temperatures are known to enhance methylation by increasing the activity of sulfate-reducing bacteria. So to wrap things up, while total and methylmercury concentration were generally low in all 14 headwater streams, we observed significant differences in total and methylmercury concentrations and loads between sites and regions. Greater percent forest cover generally corresponded with lower mercury loads over the 6-month study period, while greater wetland cover generally corresponded to higher methylmercury concentrations and loads. Landscape type also played a role in regional patterns, with sandy catchments typically having lower methylmercury concentrations and lower total and methylmercury loads than their more bedrock-dominated counterparts. That said, there were some regional anomalies, such as the higher mercury loads in Center Fire Reference 1 and in Norway 3 that require further study. So we also collected isotope samples throughout last summer and most of this one. So I'm planning to work out some metrics around how quickly water is moving through these systems and how that impacts mercury transport. And understanding these sources for variation in mercury export in undisturbed boreal forests is key, because most of these catchments are scheduled to be harvested in the next year or the next few years. And having a baseline measure in undisturbed conditions and identifying drivers of mercury export will allow us to assess how these watersheds and others like them are impacted by forest harvesting and other disturbances such as forest fires or invasive insects. And that's all from me. Thank you.
Excellent. Thanks very much, Wei. If you want to, so I'm just looking in the chat from Arsh. We have, what do you think the impacts of the forestry industry are on mercury exports?
Okay, so there actually is a fair bit of work regarding forestry impacts on mercury, but almost all of it comes out of, almost all the existing work comes out of Northern Europe. And their landscape is quite different from ours, so we can't confidently say that we'll see the same patterns here. But overall, what I'm currently thinking that after harvesting, there's a lot more open canopy. So I did mention stream temperature at the end, more open canopy, more sunlight, warmer streams. Also increased wetness from rainfall, and those wetter and warmer soil conditions create conditions that are more favorable for methylation. We're also going to see probably some water-filled cavities across the landscape from stump removal or just from driving damage. And those kind of create mini wetland-like environments that, again, create ideal space for methylation.
Great. I don't see any other questions there. I will point out that Larissa did respond to Claire and Jim's questions before. So if you wanted to check out the chat for that, again, apologies for missing that. If anybody has another question, I don't see any. We got maybe a minute left, so I've got a quick question. Apologies if you really mentioned this, but the pictures that you showed,
yeah,
the streams,
yes.
Did you have them go into a weir or a V-notch or something, or were you stream gauging as best you could across those?
Yeah, we did not have any weir setup. We had quite a number of sites out, so we were doing bi-weekly flow measurements as best we could. It was easier for some of the rockier sites where the landscape kind of created a weir for us, but everywhere else it was bi-weekly flow measurements, and we used that to create a continuous record.
And so what percentage of the, I mean, I work in peatland environments as well, up in the James Bay lowlands, and I mean, the water is just going everywhere at some points of the year. So we tried to estimate how much we were missing. How much do you think you might be missing in some of these more diffuse flows, and how would that impact your decision making?
For a lot of our sites, they are, for example, for some of the narrower streams that run through forests, I'm confident that we have a pretty solid record there. For some of the ones that are in more grassy areas, we're definitely missing some. There's a lot of beaver activity in the area as well, so sometimes our sites are flooded out. For those ones, I would say there's maybe like 30 to 40% that we're missing.
So would you consider trying to like incorporate some of those errors into your analysis, like knowing that some of your watersheds might actually have 30% more flow, where you're less confident with the discharge in some?
So we did actually exclude a lot of the watersheds that we thought that would be mostly problematic in. For example, I said in this presentation that we had 14 sites. We actually had stream gauging across 19, and we cut out the ones that we thought were the most problematic. So the ones that are in here, there still are some errors, but we eliminated the sites that, for example, had a lot of beaver activity. So this is, I think, the best that we could have done under the circumstances.
Yeah, it's
but
never
that said,
easy.
anytime you're trying to estimate loads based on biweekly sampling, there's going to be significant error involved for sure.
Yeah. Okay, thanks very much, Wai. We'll move on to our next speaker, Arghavan, talking about hydrological and water isotope characteristics of 3 mesoscale Precambrian shield watersheds in Ontario, Canada. And that is from Laurentian.
Yeah, thank you. So now I'm sharing my screen. Okay. So hi everyone. I'm Arghavan. I'm PhD student at Laurentian University, and today I want to talk about the first part of my results for my PhD. The topic of my presentation is hydrologic and water isotope characterization of 3 mesoscale Precambrian shield watersheds in Ontario, Canada. All of us know that stable water isotopes are being used in combination with hydrometric information to better understand hydrological processes and other water-related issues in watersheds. And while H2 and O18 are helpful in investigating spatial and temporal variability in hydrological processes, their application is still limited, especially in mesoscale watersheds. On the other hand, hydrologic function is influenced by landscape characteristics, but finding the most important characteristics and the way that they affect hydrological processes is a challenge. So according to this, the question that I had on my mind for my study area are there important differences in the stable water isotope framework for shield watersheds that are critical to consider when using isotope to understand hydrological functions? And how do landscape characteristics affect hydrological functions, function metrics in Central and Northern Ontario? And how different are hydrologic function and landscape drivers in 3 adjacent boreal shield watersheds? So according to these questions, the objectives of my research were determine a regional isotope framework and the spatial and temporal variability of hydrologic processes across 3 boreal shield watersheds, and quantify metrics of hydrologic function and landscape characteristics for SNF and Muskoka River watersheds, and finally classify 27 individual boreal shield catchments according to hydrologic functions and landscape characteristics. My study area, as you can see on the right side of the slides, were the combination of Sturgeon River, French River, and Nipissing, or SNF watersheds, and Muskoka River watersheds that are located in central and northeastern part of Ontario. Around 82% of the Sturgeon River is covered by forest, and around 16% covered by open water or wetlands. For Muskoka River watersheds, around more than 19% covered by lakes and wetlands. In total, the area of SNF and Muskoka River watersheds makes up 45% of the area that flow into Georgian Bay. So knowing more these areas, not only important for knowing better Lake Nipissing, but also it's important for Georgian Bay too. So for water isotope surveys and analysis, I had stable water isotope samples for river surveys between October 2013 to May 2019 for SNF and Muskoka watersheds. The samples were collected between weekly to monthly. Also, I had in watersheds rain, snow course, snow lysimeter, and groundwater samples across SNF and Muskoka watersheds that you can see the numbers here. Moreover, I used daily stream flow records. I had 8 stations across SNF and 6 stations across Muskoka watersheds that I used their data. In this graph, you can see, in this table actually, you can see the metrics and analysis that I used through my research. I can divide them to hydrological, isotopic, and landscape analysis. But today I want to just mention the most important ones for you. Also, for finding the, for classifying my 27 catchments in SNF and Muskoka, I used PCA and HCPC statistical analysis. Before using this analysis, I examined multivariable normality of my datasets by Hens-Zickrell test, and I used MVM R package for doing this. Also for PCA and HCPC, I use Facto Extra R package. Also, after all this, as I said before, I wanted to classify my 27 catchments according to their similarities and differences. And because of, for this, I generated 6 different scenarios. For each scenario, I use a specific number of variables of isotopic, landscape, and hydrologic variables that you can see in this picture. For instance, I had isotopic only scenario, landscape only, or 4 other scenarios that was the combination of all isotopic, landscape, and hydrologic variables. But today, because I don't have enough time, I can just explain the most 3 important scenarios: isotopic only, landscape only, and the most comprehensive combination of all variables together. So for results, here you can see the isotopic composition of surface and source waters for Muskoka and SNF watersheds. And the circles are representative of actual range of the values. You can see that precipitation spans the largest range of value across all watersheds, and the snowmelt exhibit the most negative values. By comparing local meteorological waterline and local evaporation line in both watersheds, we can find the impacts of evaporation enrichment on source waters across both watersheds, and also larger departure of LEL from a local meteorological waterline in Muskoka watersheds shows a higher evaporative enrichments in Muskoka in comparison to SNF. This graph shows the box plotted related to surface water sampling point, 27 surface water sampling point across SNF and Muskoka watershed. You can see that we have more variability across SNF in comparison to Muskoka, and also in Muskoka watersheds by moving to downstream, the stable water isotope values increase, or actually they prone to more positive values. Also, the least variability, we saw the least variability in lower watershed section of Muskoka watershed. That was the result of high percentages of the water body, especially lakes in this area. Also, we detect the impacts of groundwater on stream flow by more negative values in some stations with a smaller variability. After that, I generated damping ratio. Damping ratio is coefficient of variation of HO or O18 in a stream to coefficient of variation of stable isotopes in precipitation. By generating the graph, we could detect good information about our watersheds. For instance, all damping ratios are located above 101 line for SNF and Muskoka watershed, that's showing the influence of evaporative enrichment as all sampling sites across both watersheds. And also the red dots are related to sampling for SNF, and the blue ones are related to Muskoka. And you can see that these two watersheds pictured completely separate from each other in damping ratio graph. Also, the least damped stations were related to 3 in SNF watersheds that has the smaller drainage area too. And the most damped subcatchments were 2 subcatchments that were in lower Muskoka watersheds. By using this information, I generate scenario number 1, or isotope only scenario. Surprisingly, Muskoka watershed sites and SNF sampling sites groups completely separate. You can see number 1 is Muskoka, and 2 and 3 was related to SNF. And for cluster number 1, or Muskoka subwatersheds, mean of O18 and mean of H2 were 2 most important variables in clustering. You can see along with a horizontal axis, on the right side, we have most damped stations, which are related to Muskoka, and the right side, we can see the least damped stations, and also from up to down, on the upper part, we have stations with more depleted values, and on the bottom, we have stations with more enriched values. For scenario 2, I used just landscape characteristic variables, and I wanted to classify my subcatchments according to just landscape characteristics. Again, surprisingly, Muskoka catchment sites and SNF group separately with some exceptions. For instance, all the stations across SNF except the stations along Sturgeon River and South River are grouped together as cluster number 1. And for this cluster, the area of the wetlands and lakes were really important characteristics for grouping this cluster together. And for cluster number 2, which is here, South River plus all Muskoka subcatchments grouped together, and mean slope and mean elevation have significant impact on clustering these stations together. Also, the largest subcatchments in both watersheds are grouped together as cluster number 3. Finally, for scenario number 6, I used all the variables, isotopic, landscape, and hydrologic function variables. And again, Muskoka and SNF watersheds clustered separately from each other. For instance, cluster number 3, here, South River plus all Muskoka subcatchments clustered as cluster number 3. Mean slope and mean elevation were really important parameters for clustering these sites together. I should mention that they had higher mean elevation and they were steeper. Also, cluster number 1 related to SNF subcatchments, that's wetland area and damping ratios were really important variables for clustering these together. Also, you can see that along a horizontal axis, on the right side, we have sites with higher lakes area that are also more damped, and in the left side, you have lower lakes, sites with lower lakes area that are least damped too. Also, 2 stations of SNF clustered together, that drainage area and base flow index were really important features for clustering these 2 together. I should mention that base flow index was highest for these 2 stations. By all this information and results that I explained for you, the take-home messages of my research could be that the impacts of evaporating enrichment on surface water across SNF and Muskoka watersheds is noticeable, and surface water isotopes across Muskoka subwatersheds are more damped and less variable in comparison to SNF watersheds, and surface storages, lakes and wetland area, plays an important role in controlling hydrologic responses across SNF and Muskoka, and also it has an important role in the differences that we can see between SNF and Muskoka. And finally, while both SNF and Muskoka River watersheds are in Ontario Boreal Shield, in all classifications and scenarios, they are grouped separately, and their differences were noticeable. So it is crucial to consider these differences in future hydrologic studies, especially for hydrologic modeling. At the end, I should say a big thank you to all people and organizations that helped me in these 2 years, especially my supervisor, Dr. April James, and thank you for your attention.
Excellent. Thanks very much for that. I don't see any questions in the talk at this time, but also looking at the time, it is, we did start about a minute late, but if a talk comes in, or if a question comes in the next sort of 10 seconds, then we'll try to address that. If not, we'll move on to our next speaker.
Thank you.
Oh, where'd the chat go? There we go. No, I don't see any. Okay, well, thanks very much, Arghavan. Our next speaker is Kelly from McMaster, talking about after 6 years, what do we know about the hydrological functioning of the recently constructed Sandhill Fen watershed in Canada's Athabasca oil sands?
Okay, share my screen. Okay, hi everyone. Thank you for joining me today. My name's Kelly Biagi, and I'm a PhD student with Sean Carey at McMaster University. And today I'm going to be talking about 6 years of hydrological and hydrochemical data in a constructed peatland watershed in the Athabasca oil sands region, and provide some insight on overall system functioning. Before I start, I just want to thank everyone who has helped me with field work and in the lab over the last few years. They're pictured here. My supervisor, Sean Carey, and the whole watershed hydrology group, and of course our funders. So many of you are familiar with the Athabasca oil sands region, which is the red area here in Alberta, Canada, where surface mining for bitumen makes up 3% of that area, which is the yellow spot in there. And although this looks quite small, more than 900 square kilometers have been affected by this mining. During the surface mining process, entire boreal forest and peatland landscapes are completely removed and dug down up to 100 meters to access the oil sand deposit. By law, these oil companies are required to reclaim the land back to equal functioning capability. And the goal behind this reclamation is to create a mosaic of different ecosystems that will work together so that water can be eventually released back to the Athabasca River. Some of these reclaimed systems, including pit lakes, forests, and opportunistic wetlands, have existed for many years, while constructed peatlands are relatively new to the reconstructed landscape, and only 2 exist in this region to date. And this is because there's several challenges as they are complex ecosystems, so they're complex to reconstruct. For example, they need to be resilient to a subhumid environment where there's an overall water deficit. They need to be completely reconstructed in a disturbed landscape where they usually take thousands of years to develop naturally. They're susceptible to salinization as they're built upon mine waste material that's highly saline, and they should mimic the key ecosystem functions that natural undisturbed peatlands provide. And I've listed some of them there, but with especially the role they play in water regulation as well as carbon storage. So to assess this, we are studying the Sandhill Fen watershed, which is one of 2 constructed peatlands in the region. It's about 40 kilometers north of Fort McMurray on the Syncrude Canada lease. And it's in an old mined out pit called Easton Pit, and it's in the top corner there where the square is. So construction for the Sandhill Fen started in 2009, where the entire Easton Pit was filled with tailings waste materials that have really high salinity and sodium concentrations. This was followed by a 10-meter tailings sand cap. And then the sandhill fen was built on top of this. So topography was added, hill slopes that are about 3 to 4 meters tall. I've indicated them on the image here. And then in the peatland area, 1/2 meter of clay was placed, followed by 1/2 meter of peat that was salvaged. And then construction was finished in 2012 when the entire site was, when vegetation was planted. And so the whole Sandhill Fen watershed is a 52-hectare upland wetland system with a 17-hectare peatland area, which is the dark gray in the middle there, which is surrounded by uplands, which is the light gray. So there is a gently sloping upland area in the south here, as well as those hummock hill slopes I talked about. This whole watershed is instrumented with 2 eddy covariance towers, which are the red triangles, one in the peatland, one in the upland. 3 meteorological towers, which are the green squares, as well as many near surface wells, which are the blue circles, which we use to take various hydrometric and water quality measurements. And unique to this system is that a pump system was installed during construction, where fresh water can be pumped into the water storage pond, which then travels across as surface and near surface water, and then can be pumped out of the outlet. And I should mention that there's no natural drainage or outflow without this outlet pump on. And the idea behind these pumps was to try and limit any salinization and also maintain wetness. And so the overall goal of this study is to use 6 years of data to understand the key hydrological changes and patterns in the Sandhill Fen, look at how these hydrological patterns are affecting the hydrochemistry, and then gauge the effectiveness of landform design, AKA, is the Sandhill Fen watershed doing what it was designed to do, which is persist in a subhumid climate, encourage salt flushing, and support a fen peatland. The climate over the study period had distinct wet and dry years, which I've indicated on the side here. This is a plot of cumulative rain minus cumulative ET over the growing season, where positive and negative values indicate a surplus and deficit of water respectively. Wet years were classified by having really large rain events. I've indicated a couple here, but there were many more. Whereas dry years had none of these large rain events, as their storms were typically less than 5 millimeters a day. 2015 was by far the driest year, which you can see down here, which was the year prior to the large Horse River fire in the summer of 2016 surrounding Fort McMurray. So one of the largest changes we saw was a shift in the dominant fluxes in the water balance. This graph here is millimeters of water of all the water balance components over the 6 years. And in 2013, the inflow and outflow pump activity were disproportionately large in 2013. And they were more than double the precipitation, which is purple, and evapotranspiration, which is the blue. In 2014 and onwards, pump activity decreased considerably, and vertical fluxes became the dominant water balance fluxes. Deeper groundwater that flows underneath the Sandhill Fen was excluded, as its contribution is really small. However, it has important implications on the chemistry, which I'll come back to in a little bit. So this change in the dominant fluxes was reflected in the water table responses, which is what you would expect. Here we have water table position relative to the ground surface, which is 0. In this portion of the wetland here, so close to the outlet, which I've indicated with the yellow circle. So with lots of pump activity in 2013, we see a really variable water table that fluctuates above and below the ground surface, as the constant pump activity controlled the water table response. This really is not ideal, as such drastic changes in the water table are stressful on vegetation and can also degrade the peat. With limited pumping in the following years, a couple of patterns emerged. In wet and dry years, they had different water table trends, where wet years, the water table position is relatively maintained, whereas dry years, you see the highest water table in the spring following the snowmelt input, which gradually declines over the growing season. Also, with limited outflow events, the saturated storage throughout the wetland also increased, where water tables were considerably higher than when they were with the constant pump activity. And lastly, two distinct wetness areas formed in the wetland. So in the east here, closer to the outlet, we have persistent standing water, even in dry years, which you can see it never really crosses the ground surface. If we move closer to the inlet, which I've indicated with the yellow circle here, we see similar patterns, but the water table is much closer to the ground surface. So closer to the inlet, we have a near surface water table and persistent standing water closer to the outlet. So do these water table patterns explain any of the hydrochemistry? This map here is interpolated salinity, where the color ramp is electrical conductivity or salinity in microsiemens per centimeter. And we can see that every year the salinity across the site has increased, where some areas in 2018 have reached 8,000 microsiemens per centimeter. The upland areas, on the other hand, and closer to the hummocks, are quite a bit fresher and act as recharge areas. But why is the salinity increasing every year? Number one, pump activity. In 2013, the inflow pump was constantly bringing in fresh water. The outflow pump was flushing any saline water out. So it kept the salinity in the wetland relatively low, under 1,000 microsiemens per centimeter. With those pumps off, there's an accumulation of ion concentration as there's no consistent flushing of that water out of the system. Secondly, we noticed that there's a gradient of salinity within the wetland once the pumps were off, which decreases towards the outlet. And this is from evapoconcentration, which is enhanced in areas with lower water tables, which we see here. The near surface water tables in the west wetland have higher salinities than in the east wetland, which has persistent standing water. And lastly, the salinity can be attributed to some mixing of the Sandhill Fen waters with deeper groundwater that contains the tailings water. We can look at the type of water across Sandhill Fen by using Piper diagrams that basically tell you the dominant ion type based on where the sample plots in this diamond shape here, which I've added for you. So the light blue symbols here represent the chemical composition of rain and the inflow water, and the red square represents the chemical composition of that tailings water that's really dominant in sodium and chloride. So we see in 2013, a lot of the samples plot in the calcium sulfate dominant area of the Piper diagram close to the inlet waters. That makes sense. And then as the years pass, we have 2015 and 2018 here, we see a distinct shift in the chemical composition as the proportion of sodium is increasing in some samples. And some samples are starting to move closer to that red square, indicating there is some mixing with the deeper saline groundwater, which is starting to spread throughout the wetland, and thus partially accounts for the increase in salinity. So mixing these hydrological and hydrochemical patterns together, there's three distinct areas in the wetland that have formed, where water tables increase towards the outlet while salinity decreases towards the outlet. And based on the Vitt et al. Study in 2016, the only peat-forming species found in the wetland are in this midsection here where the blue is, where there's near-surface water tables and intermediate salinity, whereas the rest of the wetland is dominated by non-peat-forming species because of either the high water tables near the outlet or the elevated salinity closer to the inlet. And so overall, we see evidence that the Sandhill Fen is transitioning away from a peatland due to the high water tables, elevated salinity, and limited outflow. This may considerably influence the long-term sustainability of this system, as non-peat forming wetlands cannot perform the same function as natural peatlands. For future construction, recharge should be enhanced. We already see this a little bit in the uplands and hummocks as they have lower salinities and that water is transferred down to the wetland. A naturally flowing outlet should be a key design feature to offer a consistent flushing mechanism. And then lastly, a combination of a marsh and fen wetland may be more appropriate, which is what we're already seeing in the Sandhill Fen, where maybe a fen upgradient of a marsh could shed excess water to the marsh and have reduced interaction with the saline groundwater as well. thanks everyone for tuning in, and I welcome any questions.
Okay, if you want to stop sharing your screen there, and then, okay, we'll look to see if there's any questions that come in. So I'll just ask a quick one while
Sure.
people have a chance to type. So you sort of started addressing it at the end on what you would do differently if you were building it from scratch. Again, do you think this is a viable way of reclaiming oil sands mining?
Yeah, I think
Given
it
the
is.
cost of the project, it wasn't a cheap venture for the company, I don't think, right? So
No, it really wasn't. And also installing that pump system was really expensive. So, you know, I really don't think that's needed. Precipitation input alone has been able to sustain wetness throughout the system. But providing some sort of outlet and flushing would be key. And I think it could work. I think also, I didn't mention it, but I think the peat column could be a little deeper. 50 centimeters here is really not that much. If the peat column is a little deeper, it can maybe attenuate some of the ions as well. But I'm hopeful that it could be done.
okay, we had a question come in from Colin saying, great talk. Do you think that salinity will become an issue for peat accumulation in the long term? I'm guessing if he's talking peat accumulation in the long term, he's talking hundreds or thousands of years with no further intervention and flushing.
Sorry. So do you think the salinity will become an issue? So for peat accumulation because of the peat species?
Well, I think more like, you know, growing a proper, well, not acrotom because it's fen, but sort of, you know, like building a peatland. So you're talking about 50 centimeters of peat, you know, 1,000 years from now, would there be 10 more centimeters of peat? Or do you think the salinity would limit it and you'd only ever have a 50 centimeter deep peatland?
I think the salinity is really going to limit the ability of peat accumulation in the long term. The species that can accumulate peat really can't tolerate any sort of salinity, and even the low saline areas in the watershed are just so much higher than natural peatlands. There are some studies that have shown some peat accumulating species that can tolerate higher salinity, so maybe using those instead. But I definitely think the long-term peat accumulation is going to be, without any flushing, will not happen.
Excellent. Okay. Colin says, thanks. I don't see any other question. Oh, here we go. Carl Mitchell. Has anyone tried to go with reclamation towards something like a salt marsh instead of a fen, even though salt marshes are not the native type of wetland? Would they allow that? And I believe they would be the government of Alberta, probably.
Mm-hmm. There actually are in the region naturally occurring saline peatlands. But they are so much saltier than this system. These systems are kind of like in between a freshwater peatland and a saline peatland. So salt marshes, I think, also would be, they're typically much saltier, but some saline, the opportunistic wetlands I mentioned in the beginning, they're already salty as well. So I think
Passiflora, I think, is one of them. Is that right?
Passiflora, I think, is a natural
salt fen.
Freshwater. Sorry.
Oh, freshwater. Okay.
I think maybe they'd be open to anything, but yeah, the thing is that naturally occurring saline peatlands are a lot saltier. So I'm not sure.
Okay. Okay, in efforts to kind of keep on track, Carl says thanks. Our last speaker is April James from Nipissing University, who's also been one of our panelists all day too. Just a reminder that we'll try to announce the winners of the student awards, the Don Gray and the Campbell Sy, after April's talk. So if you are able to stick around, then please do. You might have to just give us a minute, but it's always nice to hear your name spoken rather than read it in an email from Jeff later on. So April is talking to us about the effects of mixed land use on total phosphorus transport in a Canadian Shield River. Thanks, April.
Okay, thank you. Sorry, it took me a while to get adjusted. Thanks so much. It's a real pleasure to participate in this session of excellent talks. So today I wanted to speak about or share with you some of the research that came out of Jane White's recent master's thesis here at Nipissing University. She just defended in the spring. And this is a collaboration with Marion McRae at University of Waterloo and the North Bay Mattawa Conservation Authority. So Joel Harris was there until he just recently moved to the Rensselaer Polytechnic Institute in Troy, New York. And this image here is literally, Jane ran across it. It's actually an image of the Wassee River at some point from, you can clearly see it's a dated postcard, but she ran across it in her work. So I thought it would be fun to put it here. So the challenge that many of you are familiar with is phosphorus entering streams from urban and agricultural sources and contributing to eutrophication of surface water bodies. That this issue is complex with solutions perhaps only through successful partnership between land managers, landowners, and scientists. And we specifically wanted to look at boreal shield or Precambrian shield watersheds. We're located in northeastern Ontario. The threats due to XSP are well known and highly populated in intensive agricultural areas such as southern Ontario and the US. But minimally cultivated and less popular areas in northeastern Ontario are also experiencing problems of eutrophication and cyanobacteria outbreaks. And this is an actual picture of Calendar Bay on the north or the southeast corner of Lake Nipissing. And our watershed is the major tributary into this bay, which is also the source of drinking water for the local community. So we set out to develop a collaboration with the North Bay Mattawa Conservation Authority, who has been monitoring this watershed for some time. We're focused on the Wassee watershed to invest, and we aim to investigate phosphorus loading from a boreal shield watershed with mixed land use. And so our higher goal is to understand seasonal and event controls of phosphorus export in this understudied landscape. To begin in this presentation, really, I'm going to really just focus on estimation that we've done of annual and seasonal loading for the Wassee River, the major inflow to Calendar Bay on Lake Nipissing. And so here's a map of the watershed, the delineated watershed. You can see it flowing into Calendar Bay, and Calendar Bay again is located in this southeastern corner of Lake Nipissing. The watershed's about 235 square kilometers in size. It's the major inflow to Calendar Bay. Total phosphorus concentrations are consistently greater than provincial guidelines. And so it's, of course, that, and it being an issue of source water protection, it has been of concern and of interest to the Conservation Authority for some time. We get about 1,000 millimeters of precipitation per year, 30% of which is delivered in snow, so cold winters. We're located on the Precambrian Shield, on Precambrian Shield geology. This region around Lake Nipissing is historically shaped by the Laurentian ice shield and its retreat, during which meltwaters flooded the area, creating glacial lakes such as Lake Algonquin, of which Lake Nipissing is a remnant. And we have a mix of sandy loam and silt loam soils. We have mixed land use, about 12% agriculture, 17% lakes and wetlands, with some considerable lake sizes in them, in the watershed itself, and 70% forest. All the data that I'm going to present today, the analysis of which we've done, was collected here at the site W10, which is really the Water Survey of Canada gauging station location, and it's where we installed our turbidity sensor that gives us high frequency surrogate information that we're analyzing here. There is additional information, spatial information, but today's presentation, I'll just focus on there. So from the study period for which we've got data analyzed extends from January 2014 through December 2018. You can see here the river where the Water Survey of Canada gauging site where we installed, where we had discharge data, and where we installed our turbidity probe. And this was installed first during summer periods in 2014 and 15, and then continuously for a two full year record from 2016 to 2018. Surface water samples were collected weekly to bi-weekly, depending on the year, and then during events, either using auto samplers or manually. During spring freshet, for instance, we literally kind of went down to the river and collected samples. We've got a suite of water chemistry that we generated: total phosphorus, total dissolved phosphorus, and dissolved reactive phosphorus, evaluated through Marin's lab at the University of Waterloo, and TSS samples that were evaluated gravimetrically here at Nipissing University. I'm only going to really speak to the total phosphorus today. So the objective here was to implement, to test a surrogate measure approach or modeling approach. Cold climate streams are vulnerable to underestimation of P loads. And so we are interested in assessing turbidity and discharge as alternative surrogate measures that would be cost effective compared to continuous sampling. And so we've implemented a linear and a multilinear regression analysis here. And just as a sidebar here, this is our anchoring system that we used for the turbidity sensor after testing it for a couple of summers. We used 4 different calculation methods of load. We know loads can be influenced by the approach for calculation. So we've used mean, discharge weighted concentration, linear interpolation, and Beal's ratio estimator. All of those were run or estimated using the river load code published recently by Nava et al. And then we've also done, independent of that, our high frequency regression model. So we have these 4 different methods for comparison. So for some results, these are our years of record. This graph shows 2014 through December 2018. We've got several years or calendar years that were wetter than normal, slightly wetter than normal, and several years that were 15 to 23% drier than normal. We see the highest discharge generally occurring during the spring freshet period, not surprising, and fall discharge can be quite variable depending on precipitation. So in this top panel, we just have precipitation and air temperature. In this middle panel, we have discharge, and then we have the different sampling that we managed to conduct, where fall is in red, spring is in pink, summer is in yellow, and winter is in blue. And then in the bottom panel here, turbidity, we can see these 2 first summers of high frequency monitoring, and then a continuous period here with just a few instances of periods where we are missing data. The resulting data set covers a wide range of discharge and turbidity conditions, extending the original summer-only sampling. So we can see the flow duration curve here in the top left, and then here we can see the frequency of exceedance versus turbidity as well. So we've got about 600 independent turbidity samples, 665 total phosphorus samples as part of the data set. For our water chemistry then, here I'm just displaying our water chemistry in scatter plots. Generally, we see total phosphorus, total suspended solids, and turbidity increase with discharge that we can see here in this column. Although the relationships differ by constituent and by season, we see clearly there's relationships with discharge displaying hysteresis. The turbidity TP relationship tends to support more of a single relationship across seasons. The relationship between TSS and turbidity appears linear, indicating that that optical measure of sediment in the water column is in strong agreement with the independent gravimetric measurements of sediment from the grab samples. The total dissolved phosphorus here was on average 60% of total phosphorus and ranged from below detection limits to 100%. For our regression models here, I'm just showing you two examples. We tried a suite of both linear regression using turbidity alone and then multilinear regression using turbidity and discharge. And so we have 4 models listed for each. And I've just showed you visuals here of observed versus modeled TP for model 7 and model 8, the residuals versus models. And so here, I just wanted to point out very, in a summary form, that discharge alone was not a good surrogate for total phosphorus. Using turbidity and discharge together produced the best performing model, giving us an R-squared of 0.6, which would be comparable to the other studies that we were able to find. So I'm just going to summarize here the loading. So on this panel, we have the 5 calendar years, and this would be total annual loads of phosphorus in kilograms. And here are our 4 loading calculation methods. And of course, our last method number 4 is our regression modeling approach, or surrogate modeling approach, where I'm using model 8, our best model here, which was multilinear. It had turbidity and discharge in the model. And you see that only for the last 2 years where we had the continuous record of turbidity. So the TP loading varies annually and seasonally. We get about 0.27 kilograms per hectare per year out of the watershed on average, ranging from 0.16 to 0.39. There was considerable year-to-year variability, highest loads occurring during wet conditions and lowest during drier conditions. We see seasonally the highest loading occurring during the spring freshet. So that's your pink bars here, indicating anywhere from 34 to 66% of the annual loads. Fall was extremely variable, so it can be as high as 44% and as low as 4% depending on the season or depending on the year. Of course, our true load will always be an unknown, but the regression models that we see here provide what we think is a cost-effective and comparable estimate of loading for the watershed. So some very quick take-home messages or conclusions. The total phosphorus transport was related in the WASI to transport of sediments, including discharge improved the regression relationships. The loading was similar to other mixed land use streams with similar igneous geology and climate. So the WASI generated that, on average 0.27 kilograms per hectare. A recent study from Finland, Tatari et al., had a range of, across their systems that they measured 0.2 to 0.3 kilograms per hectare per year. We see larger 3 to 7 times the amount of phosphorus coming out than forested studies. Again, I'm referencing the Tatari study and Winter and Dillon in central Ontario, which generated on the order of 0.06 to 0.09 kilograms per hectare per year. And we're much lower than intensive agricultural land use streams. The spring and fall were especially important for TP transport. And so the work that we did with the Conservation Authority was, I think, particularly useful in that we were able to extend the original data set that was purely summer base flow sampling. So this site seems to straddle forested land use, igneous geology sites, and agriculturally impacted landscapes. The future directions we'd like to develop further is to dig into the additional water quality data, the different species of phosphorus or different compartments of phosphorus, as well as water stable isotope data set that we've developed to evaluate sources and flow paths. And we also have some additional field sites within the watershed that might allow us to do more of a spatial assessment of phosphorus and where it's coming from. Thank you very much.
Excellent. Thanks, April. I love the XKCD cartoon in there. The full version, I think, has another 12, maybe 9 to it. So I do encourage anybody who likes XKCD to go check out the regression plots on there. Colin has a question. Very interesting work. Do you have an idea of what is driving the extreme variability in the fall?
Yeah, that's a good question. I mean, I think we can see that relationship that we've built really strongly depends on that fall data, right? And so this is where I think it's going to be really interesting to look at the more spatially collected data set, where we've got a couple of tributaries upstream. One, we know from some of the spatial data, the conservation's collected over time, and then we have an additional year of intensive weekly data that we've collected. One of the sub-watersheds is particularly high in phosphorus. We've also got some surface water lakes, or some significant lakes above us, the Wassy Lake and Graham Lake, and that exist. And we're hoping, we've published already a study looking at stable water isotope signatures, and we can see that water looks strongly enriched over the course of, by the time you get into late summer, early fall. And so I'm wondering if, I'm not answering your question, but I'm really excited to look at the data set to see if we see, for instance, the influence of, surface water, for instance, mobilizing or lakes and wetlands with that evaporative enrichment signature, in addition to what's happening to phosphorus. But I'm kind of speculating at this point.
Excellent. If you want to stop sharing your screen there, April, we'll go back to. So I do have the results, so we don't need to hang around too much longer. I would like to just thank the tech support with Daryl and Dieter Didar from the whole series. I understand they've been pretty good at booting out a few people that weren't supposed to be in maybe some of the earlier sessions, and then also meeting with the speakers prior to make sure that it ran fairly seamlessly. From what I gathered, it was pretty seamless. So that was good on that end. This being our final sort of conference of the year, I wish everybody a safe and happy COVID fall, depending on what your classes and teaching looks like. I know we're completely online here in Brandon, so trying to get sort of 4 courses up and running this fall will be a bit of a pain. So for the Campbell Scientific Best Student Paper for poster was Jason Karras-Allen from Dalhousie, and he wrote on the lagoon thermal sensitivity and groundwater-derived thermal buffering of coastal habitat in a context of climate change. And for our Don Gray speaker, which was just actually our penultimate speaker this afternoon, was Kelly Biagi, who, if you don't remember from a few minutes ago, spoke about the reconstructed Sandhill Fen watershed and what we know about the hydrological functioning. So hopefully Chris Spence can reach out to you to get an address to send you a check. If not, then you can send Chris or myself, or really any of the executive, an email to get that information to them so that we can send you a check, although getting the checks signed might also be slightly more complicated. So, your check's in the mail, if you will. We're good for it, we promise. We'll try to get it out to you as soon as possible. So yeah, anyway, if there are any other questions or comments, concerns, you can throw them in the chat right now. If not, again, a safe fall semester for everybody, and hopefully we will see you in Banff in May in person, although I'm not optimistic personally. I would love to go though. So I'll just hang out as people disappear, but if there are any questions or concerns.